Assalamu alaikum. Welcome, students. In lab session 1, we briefly introduced the environment of Matlab and some basic commands or functions most commonly used. In this lab session, uh, we will model a simple mechanical system with only one degree of freedom using state space representation, also known as time domain modeling, and then we will solve the resulting state space representation using Matlab script. So here is the mechanical system considered for analysis. As we have comprehensively covered how to write equation of motion at the node and how we can arrive at state space representation from equation of motion of any system in theory lectures. I will be brief here. Um in this lab session, two versions of this same system are modeled. First one is without spring, and the second one is with spring. So I am removing spring from here to model the first case. So this circuit system will become like this. Damper. Sorry for my bad handwriting. This will become x a of t, and this will become f a of t. So equation of motion at this node will be, I'm using x here instead of xa, so fa will be equals to m d square x over dt square plus b dx of dt. Equation 1. Now this system or equation looks second order, but I can choose velocity instead of this displacement to make it the first order. So uh, removing this variable, so it will become, equation 1 will become m dv over dt plus bv, or dv over dt is equals to fa over m minus b over mv. So this will become equation number 2. Now we will use MATLAB to solve this equation by considering values of m and b. This system has only one state variable, which is v here, as it is a first order system. Now let's write the MATLAB script for it. We will use MATLAB ODE 45 function to solve the differential equation. There are various differential equation solver present in MATLAB with their pros and cons. I'm not going into the details of this. I'm just using ODE 45, which has pretty much good accuracy for solving the differential equation in our case. Uh, let's go into the help section of the MATLAB to see what are the inputs and outputs of this ODE 45 function. Uh, Now here you can see this ODE 45 function takes three inputs. One is ODE fun, second is T span, and third input is Y naught. Uh, Whereas the outputs are T and Y, which are of course the One is the time variable and second is the output y variable. So let's check out what this ODE fun is. This It's actually a function handle which defines the function to be integrated, or we can say to be solved. If we consider this differential equation, uh, then syntax for writing the function handle is like this. Function, it's a generalized way of writing a user defined function. So here the output is dy dt is equals to name of the function and the two inputs which are t and y. And the differential equation is y dash is dy over dt. So here the output is dy dt is equals to 5 into y minus 3. So the second input in this function is tspan. So tspan is the interval of integration, and the third input is y naught, which is the initial condition of differential equation. So now let's write the function handle new script. I am saving this script with a name. Sorry, mass damper dot m. Now I am writing the function handle function. We have output dv dt in our case, so I am writing dv dt is equals to name of the function. I can use any name of my choice, damper, and the inputs are t comma v. As we need to plot the velocity variable with respect to time. So the inputs of the function handle as defined as we see in the syntax was to write the output variables or the variables that needs to be solved must be written in the function handle like this. And assume that the value of mass is 750. I'm roughly assuming it. Value of damper is 30 and the applied force is 300 newtons. So the differential equation will be, here we have grabbed it, dv over dt is equals to fa over m minus b over m into v. So dv dt is equals to fa over m minus b over m into v. So now we have written the function handle. Now we will write another script in which we will call the ODE45 function. So I am writing another script, saving it with a name, uh, untitled, whatever it is. The output of the ODE fun is t comma v. ODE 45. Sorry, ODE 45 is t and v. We will write the name of ODE fun, which is in our case is mass damper. So MA mass damper. You have to strictly follow the name of the function here. If you have you can see I have written just like I have defined here, mass underscore damper, and the name of the file which we have saved is also mass underscore damper dot m. So you have to keep it in your mind. Second is the t span. I want to plot this t comma v from 0 to t 200 and assume that the initial condition is 0. Now I have after the execution of this function, we will have values of v and t. So we need to plot the values of t and v to check how the response look. So I'm plotting plot t comma v grid and give title. It's optional, not mandatory. Title to the figure: velocity of mass damper system. Uh, Now let's save it and execute. Now here is the plot of mass damper system of the differential equation. Now here you can see the time span is from 0 to 200 as we defined in the t span here. So you can change this time period, time span of your, and you can use any time span of your choice. So here you can see the system is the first order, so there are no oscillations. You can change values of m and b to check the this system only changes its speed, and nature of the plot always remains the same, which is the exponential. Now moving towards the next version of figure, in which spring is also added to the system. The figure will become spring damper mass. This is the reference. Values are B, K, and M. Now writing equation of motion. Fe is equals to m d square x by dt square plus b dx by dt plus kx. Now assume state variables. I'm quickly doing it. X1 is equals to x, one state variable, and x2 is equals to dx over dt. So putting these assumptions in this equation, so first state equation will be uh, fa is equals to m dx2 by dt plus bx2 plus kx1, or I'm directly writing it dx2 by dt is equals to fa over m minus b over m x2 minus k over m x1. This will be the first state equation, and second state equation will come if we substitute equation 1 in this equation. So dx1 by dt is equals to x2. Now we will solve these state equations in a similar way as we did in the previous case. Now we will look in the documentation of ODE 45 uh, for how we can solve the two simultaneous first order differential equation, also known as state equation. ODE 45. Uh, Now, here they have considered two system of equation as an example. The procedure for writing is almost same, except now they have created a column matrix of two rows, also called vector here, and wrote these two differential equations in rows of the vector. So we will follow the same procedure in writing the function handle for this case. Here you can see y dash 1, which is dy 1 by dt. So dy dt bracket 1 written, this is written here as like this, is equals to y1. So here is y1 written like this, plus 2 into y2. Here it is like written like this. Similarly, dy2 by dt, which is y dash 2, is written like this, and so on so forth, the whole equation. So we will follow the same procedure in writing the function handle in our case. So I'm writing it. First, save the script, like mass, damper, and spring. As we have all three elements, this name of the file is up to you. You can use any name of your choice, but you have to remember, use the same name while while using this function in ODE 45. So function, dx dt is equals to mass, damper, spring, t comma x. Uh, Now I am arbitrarily assuming the values of MBK 705 kg, B is equals to 30 units, and K is equals to 15 units, and the applied force is 300 Newton. So first create the column vector of two rows and one column. Dx dt is equals to zeros, and initialize them with zeros. So this function creates a vector of sorry, a matrix with two rows and one column, and initialize it with 0. So first, in our case, equation 1 is, first equation is dx dt 1 is equals to x2. So dx dt 1 is equals to x2. Second equation in our case is dx 2 by dt is fa over m minus b over m x2 minus k over m x1. So fa by m minus b over m into x2 minus k over sorry, k over m into x1. Uh, Now here we have completed the save it. Here we have completed the function handle. Now let's write another script to use this function handle by calling ODE 45 function. So I am saving this script. T comma x variables will remain same as we use it here. ODE 45 bracket, name of the function mass, damper, spring, time span. I'm considering the same time span, 0 till 200. comma initial values. Mm, Now we have defined two initial values as a column matrix or vector, as we have two differential equations. I'm using the same subplot command as we did in lab session 1. Uh, Now I have created two areas with two rows and one column, and I'm using the first area of the figure. Plot t comma x. uh, Now just take this instruction for granted. I will describe it later after the execution of this script. Uh, X label, the the x-axis in our case is time, and y label, since we are plotting x1, and here we have in our assumption x1, we have considered as x1 to be x, which is the displacement of this mass. So I am writing here y label as displacement. Now subplot, I'm copying this whole piece of code, paste. Now subplot to x2. Now x2 is in our case, in our assumption, x2 is equals to dx over dt, which is the velocity of this whole system. So I'm writing here velocity in case of displacement, and the x-axis will remain the same, which is time. Now save this script. I am executing this script. Oh, now as evident from the plot that this system will come to rest as the velocity is zero after some time, maintaining a constant displacement which is 20 units from its reference. You can also make an observation here that it is very difficult to predict the type of response which we have learned uh, in theory lectures just by looking at the values of MB and K. But in case of frequency domain analysis, or also known as S-domain analysis, we can find out, or we can comment on the type of the response just by finding the roots of the poles of the system, if we can relate M, B and K with poles. So here it is difficult, so frequency domain analysis proves to give an advantage over this type of analysis. Now let's describe why I have written like this and this to access values of x1 and x2. For this, just look x variable in the workspace. I'm double clicking it. You will get this window. Here you can see the x variable is a matrix having two columns and multiple rows. So the first column of this matrix represents values of x1, and the second column of this matrix represents values of x2. So if I want to access value, for example, the value of this element, I can access this element by giving the address 1 comma 1, which is first row and first column. This element has an address of second row and first column. This element has an address of third row and first column. So column is same. So if I want to access all of the first column, all of the entries of the first column, as is the case in our case, so the procedure is put the colon instead of numeric value. So if I am writing colon here, so this means I am accessing all the row entries, and comma 1 represents first column, so it will access all the entries of rows present in the first column, which is x1 in our case, and it will access this type of a variable. This way of writing variable will access all the entries of the rows present in the second column, which is x2 in our case. So this is x2 in our case, and this is x1 in our case. Now that's all about lab session 2. You will find a table at the end of this lab session here, in which you have to make observations by changing these parameters one by one. You have to change mass by keeping all other parameters here constant, and you have to observe the changes in displacement and velocity plot here in this code. This is the plot for M is equals to 705, B 30, K 15, and FA 300. So you have to change the values of mass, keeping all these to be constant, and observe the changes here and here in this figure. So you have to do this activity one by one. First, you have to change mass, keeping these constant. Then you have to make this constant and start changing this value, which is the damping B of the system, and observe the change in displacement and velocity plot. Similarly for a stiffness, which is spring, and also for the applied force. You have to change observe the change and describe you have to describe the changes in your own words. I will formally make a question for it and will upload it in Google Classroom. So that's all about today's lecture. Thank you. Allah Hafiz.